All right, so for chapter 26, we started talking about in class some of the scenarios around how it starts out in 26. So I'm going to give you some notes, and then when you come to class, we're going to work on some problems. But chapter 26 is all about what we call chi-squared tests, C-H-I, chi-squared tests. And the first chi-squared test we're going to talk about is called a goodness of fit test. Goodness of fit. And so if we think about goodness of fit, how well does a distribution fit some distribution that someone claims? How good does it fit? All right? So, chi-squared goodness of fit test. My null hypothesis that I come up with is that the data, so our data, is distributed the way that it is expected. So there's always an expectation of how things should be distributed, whether it's based on ethnicity. So what percent are white, black, Hispanic, Asian Pacific Islander. The M&M factory distributes by color. Are the distribution of the M&M colors the way that it is expected? And expected can be from a factory, it can be from a national statistic, it could be from, again with the example of the Greece district, from the way that the distribution of ethnicities is within the Greece district. But the null is that it is distributed the way that we expect. So what are we trying to find evidence for? We're trying to find evidence that the data is not distributed the way that it is expected. All right, so we're going to assume that it is, and we're going to try to see if it's different than what we expect. And so the HO and the HA for this chapter is not numerical, it's written in words. The distribution of the students at Pinebrook is what we would expect, matches the district's distribution of ethnicities. Alternative, the distribution of the students at Pinebrook is not the way that the district is distributed by ethnic origin. Okay? Now, the formula for chi-squared is different than we have. And it really is the same formula that you guys use with science around percent error. It's the difference between what we observe and what we expect to happen. But we take that value and square it so that way we get all positive differences. Divide that by what we expect to happen and take each of those values and add them up. Okay? So it is the sum of the differences squared divided by what we expect. So it's similar to a percent error calculation. The degrees of freedom is n minus 1, where n is the number of categories that I'm comparing. It's not your sample size. So if I'm comparing the categories of ethnic race of white, black, Hispanic, Asian Pacific Islander, I got 4 categories. My degrees of freedom then would be 3. All right? Conditions. No longer do we talk about randomization. Okay? The first condition that we talk about is the fact that the data that we're working with needs to be in counts of how many. You cannot work in percentages. If you have percentages, you have to calculate how many. So the data has to be in counts of how many. Okay? How many? We still have an independence and population greater than 10 times sample size condition. And the last condition here, again, now is our sample size large enough? But how do we measure that? Are all expected counts greater than 5? All right? So we have to figure out how many we would expect to see, and we have to make sure that they're all greater than 5. They give you a little bit of leeway, though. The leeway is if no more than 20% of the categories can miss the mark. So in other words, if not all are greater than 5, no more than 20% of the categories can miss the mark of 5. So let's say there's 5 categories. Well, 20% of the categories would be one of those, because 1 out of 5 is 20%. So if one of your categories misses the mark, it's okay. No more than 20% can miss. So let's say you had 5 categories and 2 missed. 2 were not bigger than 5. You didn't take a big enough sample size. You need to go back and take a larger set of data. Okay? But if you do meet all the conditions, we say it's okay to do a chi-squared goodness of fit test, or what on your calculator it'll see listed as GOF. Listed as goodness of fit. You will not see this on your calculator if you use the black TI-83. You will see this on your calculator if you use a TI-84. All right? So how do we run this on the calculator? Well, on the calculator, in list 1, you put your observed numbers, your observed counts. In list 2, you put all the counts that you would expect. How many do you expect for each of those categories? And in list 3, all right, this is list 3, but it's list 1 minus list 2 squared divided by list 2. So this is list 1 minus list 2 squared divided by list 2. And then you hit enter and it will do all of that work for you. Your chi-squared value is the sum of list 3. So when you add up list 3, that's what this is, list 3. When you add this up, then you get your chi-squared value. And then you have to go to your chart if you're using a TI-83. If you're using a TI-84, you're going to run the chi-squared test and it will give you your answer. Okay? And then from there, it'll give you a p-value, and then you write a conclusion. All right? So you'll have a chi-squared value. From the chi-squared value, you'll have a p-value. From the p-value, you're going to write a conclusion. The thing that's different about chi-squared is because it is the differences squared divided by what you expect, these numbers get to be fairly big. So if I had a chi-squared of 7, you think, oh, a z-squared of 7 is way out there. Not a chi-squared of 7, though. Not a chi-squared of 7. So depending on how many degrees of freedom you have, sometimes numbers that you think are big really aren't too big at all. And so let the chart or let the calculator give you this p-value number, and just whatever it says you go with, and then you can write your conclusion. So that's it. So when we come to class, we're going to work on some problems.